morning. Last few classes we have been discussing about phase equilibria in a binary system, and we looked at several types of binary phase equilibria that are possible, and in binary system we have seen that maximum number of phases that can stay in equilibrium is 3. Now, today we will look at phase equilibria in a ternary component, where number of component is 3. And let us see under this case what we are going to consider. Say in a 2-dimensional space, the representation of composition was quite simple. We can construct the diagram easily, but when we go to a next higher order, we need to define a method of representing composition. We will talk about composition triangle, how do we represent composition in a ternary system. We will look at ternary isomorphous system. We will look at some of the 2D representation of ternary diagram. This is done through different sections like horizontal and vertical sections. We will look at one ternary system where we have eutectic reaction or ternary eutectic. We will look at horizontal and vertical sections of this ternary eutectic system, and from this we will see that complication, if you go to higher order, it will be impossible to represent it in a 2D. There the only way we can extend or understand phase equilibria is through mathematical models or computer simulation. So, this is what we are going to cover today. Let us begin this lecture with composition triangle, which is shown over here. So, we use an equilibrium. This corner represents pure A, this corner represents pure B, this corner represents pure C. And now, say this triangle we can construct like in a 2D graph, several these lines can be constructed, and these lines which represent composition in some way, we will come to it little later, and say like these lines which are drawn at equidistance, they represent actually the percentage C. Like here, if you look at this point, percentage C is 0. Say suppose we go to the next, let us say it is 10, 20, 30, 40, 50, 60, likewise it becomes 100 over here. And the same way, these lines which are drawn parallel to the side opposite the vertex A. So, that is C B parallel to this, these lines represent percentage A. Similarly, lines drawn parallel to the side opposite vertex B. So, that means AC, all these lines parallel to AC, they represent percentage B, and this end is 100%, this end is 0. So, now let us look at how do you represent. So, what will be the composition of this particular point. Now, here you can read it easily. Say suppose you want to read what is the percentage A. So, here this way you will read from this end. So, here it is 0, 10, 20, 30. So, A is 30. Similarly, how much is B? B you check up from here. 0, 10, 20, 30. Now, you check up that whether that how much is C. So, C should therefore be 40, 20, 30, 30, it makes 60, C should be 40. Let us see what is C. So, you check up from here, this is 0, 10, 20, 30, 40. That means, you add up all, you get 100. So, in fact, this is easily seen over here, that means percentage A is represented by that this to this. So, actually it is C q. Similarly, percentage B is represented by P x, which is actually equal to. So, this is an equilateral triangle. So, P x equal to P q, and percentage C is A p from here, from this point to this point, which is equal to A p. And so, therefore, you add all these up, it comes to 100. Now, having done this, let us look at a ternary isomorphous system. Now, which is shown over here. See, this is the composition triangle. Now, in this case, each of the binary system also must be an isomorphous system, which is shown here. See, we have opened up, we are trying to represent this in 2D. So, this is the composition triangle, this point is pure A. Now, on this, if we draw a perpendicular and here a perpendicular and draw the binary phase diagram between A and C. This portion is liquid, this is the solid solution alpha. Similarly, we do the same thing over here. So, this melting point, melting point and this, they are exactly same. So, if you say suppose here you cut this diagram and try to fold it up. So, what will happen? Then this point and this point, they are exactly same, they will meet each other. Similarly, you cut out this portion and then this and this point, they will join together, and similarly these two. So, what you will have, if you do this, you cut out this portion, draw this on a 2D diagram, cut out this portion, fold it along this and make this vertical. Then this point will join here, this point will join with this, and these 2 points will come over one another, and in that case in a 3D what you will have? You will have one surface, top surface, which is made up of these liquidus line. This line is liquidus and this line is solidus. So, this liquidus represents the temperature at which solidification begins, and here solidus represents the temperature at which solidification is completed. And now, let us see how does this 3D diagram look like, which is shown over here. Now, if you do this folding, so this is the top surface, this is the top surface which is drawn by firm line. So, whatever you see, say this line these are, let us say, different isotherms. So, this is the top surface which represents this surface, this top surface represents liquidus. Similarly, you can think of this bottom surface joining this liquidus line, this solidus line. This is the solidus line, and the other solidus line, which won't be visible in now 3D, it is covered by the top surface, and if you join these bottom surfaces, so this line and this line, so it will generate a curved surface, and this surface is called solidus. So, you see 3D, it is now quite difficult to now visualize that at particular composition and particular temperature, what will this system consist of. For this, what we do? We visualize, we take certain sections. Say suppose we try and draw an isothermal section, say at this particular temperature. So, imagine this is lower than this triangle, this plane here. We draw a plane, a horizontal plane. Horizontal plane means an isothermal plane. So, this vertical axis represents temperature, this is the melting point of A, and this is an isotherm. This is a plane, this dotted line here, this represents a plane which intersects this temperature axis below melting point of A, below melting point of C, but it meets the other axis above melting point of B. In that case, clearly you can see, said here this will towards this. So, it will intersect, where does it intersect these two surfaces, which is shown over here. Now, look at so one end you will find when this surface cuts like this, I think there is some AC portion will be solid. So, it will one side this one will cut the solidus line. So, this is A and C. So, this plane first, this is that solidus line, this is B, and B end, AB end is still liquid. So, this part here it intersects somewhere here, maybe here and similarly here. So, which is drawn over here along. So, this portion is yet to solidify, whereas this part has solidified, and this is the region, and you will get a region where I think there is this diagram actually represents a section somewhere above the melting point of A, somewhere here. So, that means this temperature is lower than melting point of C, but this temperature is greater than melting point of A, and also greater than melting point of B. So, here you can see that this will section say that this part is the liquidus and the bottom part is the solidus, and this portion, this side, it will be liquid. Now, here look at this condition where two phases are coexisting together. If you apply phase rule, then what do you get? Now, this is a ternary system, number of component, this is 3. So, this equal to 4. Now, number of phases coexisting P is 2. So, therefore, degree of freedom here is 2. Now, 1 we are fixing the temperature. By fixing the temperature also, we are not able to define this two phase region, unless we put, there is one more variable which needs to be fixed up, which is this tie line. So, that means either you have to fix up, say my liquid has this composition, then you will be able to calculate what is the composition of the solid, which is solid becomes fixed, or else you have to say that solid has this composition, then the liquid becomes fixed. So, this is so therefore, so this we will see later when we will talk about how we can apply the principle of thermodynamics to calculate this phase diagram. Now, next let us extend and see that how will the vertical section look like. Now, here in this diagram, think about a vertical plane which intersects this composition AC at this point, which is let us say this point, which is 20% C, 80% A. Similarly, this point is let us say 20% C, 80% B. Now, if you construct this, you will see that at the highest temperature it intersects here, excuse me, which is shown over here, and then this is where solidification begins and this is where the solidification is complete, and this portion is liquid, this is alpha, this is liquid plus alpha. So, same way here also you will find it will intersect a liquidous surface here and the solidus surface at this, and in between here at any composition you can see that any composition. So, this is your this is where the solidification starts, this is where temperature where solidification is complete, and all along this composition line the percentage C is same. What is changing is the ratio of A and B. So, here it is 80% A, here it is 80% B, somewhere in between it may be 0.2, 0.4 A, 0.4 B. So, there you can read from this diagram this melting range of that particular alloy. Now, let us see take up the case of a simple ternary eutectic. Now, see in a ternary eutectic what happens in a binary eutectic, we have seen that a liquid breaks down into two solids alpha and beta. Now, in case of a ternary eutectic, there will be liquid of a particular composition will decompose at the same temperature into a mixture of three solids. This is ternary eutectic. This is the ternary eutectic. Now, let us see that how do we construct a ternary eutectic diagram. Now, here let us take up a case where each of these binary, they are simple binary eutectic. This is the binary eutectic isotherm, this is the binary eutectic isotherm for system A B, this is the binary eutectic temperature for the system B C, and this is the binary eutectic temperature for the system A C. Now, here also what you do is here also you cut out this portion and fold it along this line, and now you imagine this is the liquidus line. Now, this point will join with this. So, one liquidus surface will drop down from that vertex that C like this. Similarly, another liquidus surface will drop down from that vertex at A somewhere here. Similarly, the third one from the melting point of B, and they will all meet at that eutectic point, and which is shown here. So, that means this is the liquidus surface, this is the projection of the liquidus surface on an horizontal plane. If you look from the top of this, it will look like as if this is a surface which is coming down, this is a surface which is coming down from the point over A at the melting point of A like this and like this, and they will all meet along these lines, these curves, along these curves they will meet, and this is the ternary eutectic point. This point is the ternary eutectic. ternary eutectic. Now, in a ternary eutectic, if you apply in this case, so this is the temperature, it will take place at a definite fixed temperature and the composition of alpha, beta, gamma will be fixed. Let us see what do you get if you apply phase rule. Now, here this component, this is 3. So, this is 4. Now, how many phases you have in equilibrium? Now, number of phase when this eutectic reaction takes place, 4 phases are coexisting. Now, if 4 phases are coexisting, in that case your degree of freedom, this becomes 0. That means, composition of liquid and each of these solid phase will be fixed. And later on we will see, we will do a simple solve a problem to show how to find out that eutectic temperature, assuming the solution that liquid solution to be ideal and assuming there is no solubility in solid state. Now, let us look at this diagram, the nature of this diagram, which is here. These are the 3 axes. Here you look at, this is the liquidous surface which is coming down from that melting point. See, on this line is the TMA is the melting point of A. This is the liquidous surface, this line similarly consisting of this. So, in this if you look at here, this line, this surface, this, then this line, this surface, this is one phase, liquidous phase. Similarly, there will be one consisting of this, and then this, then this. Similarly, a third surface will be from the melting point of B, and 2 of these they will meet along a line like this, a curve like this. Similarly, this surface, one coming down from melting point of B and one coming down from the point TMA, they will meet along this. So, there will be 3 curves along which these surfaces will meet, and inside I have drawn this is the isotherm, this triangle, say 1, 2, 3. This you can say this is the temperature, eutectic temperature, that is isotherm at eutectic temperature, where all these are meeting, and these are the fixed composition. This is the alpha, this is beta, and this is gamma, and they have fixed composition. So, at this temperature T, that equilibrium, there will be equilibrium between liquid of specific composition with 3 solids of specific composition, that is 1, 2, 3. Now, let us try and construct say sectional diagrams. So, now let us look at one isothermal section. Isothermal section, and we are taking it at a temperature T which is lower than each of these melting temperature. This is lower than melting point of A, this is also lower than melting point of B, and lower than melting point of C, but it is greater than the eutectic temperature. Now, here in that case, say this is the plane here which is drawn, this is the plane. So, 1, this is 2, this is 3. So, here you can see this plane will intersect this somewhere here, this line somewhere here. So, this is the liquidus line A n. So, this is one point, this is one point. So, this is the liquidus line. So, you get this is the liquidus line. Similarly, this plane will intersect this line here. Similarly, and similarly the solidus this, and there will be another here. So, these two, and this will be the solidus, this is the liquidus, and here you will have alpha plus liquid, and here you can also draw tie lines. So, you have to specify the temperature of the solid which will be equilibrium with the liquid. So, similarly, there will be such two phase region on each of these three ends. This will be liquid plus gamma, this portion is liquid, this is alpha, this is beta, this is gamma, this is liquid plus beta. Now, let us see, having done this, let us look at the isothermal section at a temperature which is lower than each of these three eutectic temperature. There are three binary eutectic temperature. So, we are taking a section at a temperature which are lower than the binary eutectics of each of these three system, but higher than the ternary eutectic isotherm. Say little over, the temperature is little greater than the ternary eutectic, but it is temperature is less than each of these binary eutectic, say A B eutectic, or it is less than B C eutectic, less than A C eutectic temperature. Now, here it is very easy to visualize, because each of these end A, B, C, there will be a region where it will be single phase. So, this is alpha, this is beta, this is gamma. Now, similarly, here there will be some of these points, there will be regions where there will be only alpha and beta coexisting. Say the end, say we are taking, say suppose here this will be alpha plus beta, and this is the portion which is liquid. This portion will be alpha plus gamma, this portion will be gamma plus beta. Now, here we will see that why this type of a triangular region should exist. This portion will be alpha, beta, liquid. So, this is the composition of alpha, beta, and this is the composition of the liquid. Now, this portion will be alpha, gamma, liquid, this portion will be gamma, beta plus liquid. And these regions will be binary region alpha plus liquid, this will be gamma plus liquid, this will be beta plus liquid. So, in the same way, I think it is possible to construct or visualize from this type of a ternary eutectic diagram, or you can construct a model and try and verify whether you get this kind of horizontal sections. And here is a horizontal sections at a temperature below the eutectic temperature. So, that means, this horizontal section is below the ternary eutectic. Let us say at room temperature, this is the alpha end, this is the beta, this is gamma, this is alpha plus gamma, this is alpha plus beta, this is gamma plus beta, and in this region you have the eutectic, that is ternary eutectic will be there in this region, alpha, beta, gamma. This portion you will get binary eutectic, alpha, gamma, gamma, beta. Now, let us try to understand how can we draw a vertical section. So, for that it is that 3 phase region, that is between that binary eutectic to ternary eutectic. It is necessary to visualize what is the nature of this zone, and we will see in the next 2 diagrams. Say here it is exactly the same diagram we have drawn here, and we are trying to construct a vertical section which is taken from along the vertical plane constructed on this line, and to construct this we have now to visualize where these surfaces are intersected. Say here first one is very easy to see, that one, say this is the point that liquidous surface is intersected. Let us say this is 80% 0.8 A, 0.2 C, this end therefore will be 0.2 C, 0.8 A. Now, so this point we can easily visualize, and then these two liquidous line, they will drop down like this. This also will come like this and meet somewhere on this along that curve where both the surfaces are meeting. So, this two it is easy to visualize. So, this is the liquidus. So, this is the point where it intersects, this vertical plane intersects this curve, that this curve along which these two liquidus surface intersect. Now, to understand what will happen beneath this temperature region. So, obviously, there will also be a temperature here, it will intersect the solidus here, and this will be the curve which will follow the intersection with the solidus line, solidus surface. Now, to visualize that, you think about here in this diagram we have removed this portion just to understand what is the nature of this 3 phase region. So, this let us say that this is 2 part, only I have just changed that orientation a bit. Say suppose this is A, this is C, this is B. So, this is a binary eutectic between A and C, this portion is alpha, this portion is gamma. So, now look at this here. Here binary eutectic, this is a line. Now, when this surface comes down, it follows, it builds a surface, a curved surface consisting of which comes down to that eutectic isotherm. This point, this represents that eutectic isotherm, this triangle, this is the eutectic isotherm. This I am still drawing as a dotted line, which you will not be able to see. Now, this surface, this point comes down and meets along at this point, which is the ternary eutectic. This is the ternary eutectic TE, ternary eutectic point, and this point represents solubility limit, and this solvus line, it also comes and meets the isotherm at this point. Now, you see, in that case what you generate here at this is one isotherm, this is one point, this is intersecting here, this is intersecting. So, this kind of a triangular region, and these are the dotted line which is behind you. Similarly, this is another at this point it just meets that eutectic isotherm. So, this type of a triangular that plane it just comes down and meets that ternary at ternary eutectic isotherm. So, with this we come back to this diagram. So, what it shows is below this point, this is that section where it, and this is the ternary, that isotherm, and this will meet at this point. If we come back, similarly, there will be a similar surface which is coming down from that AB eutectic, and they are meeting at this point. So, somewhere here they will meet, and this isotherm here they will meet. So, that vertical section will something look like this, and which is what is drawn here, alpha beta liquid, this is that, and this side will be alpha gamma liquid, this side will be beta plus gamma plus liquid, and this is that eutectic reaction isotherm, and after this you will have the remaining liquid will solidify as ternary eutectic, but you will have primary phases depending on where you are located. You will have some primary alpha, you will also have some binary eutectic and ternary eutectic. So, this is how it is possible to construct the both horizontal and vertical sections of a phase diagram. But the problem comes, real systems are never just binary or ternary. Say even simple any alloy you take, you may have 3, 4, 5 alloy elements present. Now, in that case, how do you extend that concept to a normal, a common, basically a binary, I mean higher order systems, where number of components will be much larger, will be larger than 3. Definitely, as a ternary diagram, it is possible to visualize or construct the diagram in a 3-dimensional space, but even if you go to a quaternary system, it will now become impossible to do so. And only way you can do this and do some calculation is in mathematical space and imaginary, say n-dimensional space, and how we will look at some example how it is done, just the basic principles. So, higher order phase diagrams, where n is the number of component, you need n-dimensional space to construct the diagram. Now, let us see, even if a simple isomorphous system, if we are trying to construct a phase diagram using mathematical techniques, how do we proceed? We looked at it, say suppose we say that I represents a particular component, and this I extends from, let us say, 1 to n. And if we assume the solutions are ideal solution, then we can say that the free energy of the system, that mixture, will be represented by these. These are the standard state free energy, this is the free energy of mixing. Similarly, you will have a similar expression for solid. So, such expression it is possible to write down, and say suppose we consider an isomorphous system in n dimensional space, and it is possible to do and visualize if such a system exists, what will be the phase composition at particular temperature. Now, an extension of this, say suppose we look at ternary isomorphous system. Say suppose I 1 represents A, I 2 represents B, I 3 represents C. We had done a similar calculation for binary. Extend the same thing to a ternary system. If you look back your lecture, if you equilibrate the chemical potential of A in solid and liquid, it is possible to write down, that is equilibrium, that is chemical potential of A in solid, that is alpha, N A is the mole atom fraction A in alpha. This is equal to this, N A L is atom fraction A in liquid. This is the enthalpy change of melting or fusion. This is the temperature difference between the temperature of interest and the melting point, and T m A is the melting point of A. And what we have seen, we have introduced, divide all this R T, and we said that this you assume that suppose this is a function A, which depends only on the thermodynamic characteristic, that is enthalpy of fusion or latent heat of fusion, the melting point and the universal gas constant and the temperature. So, this in that case you can simply write this expression in this form. So, this is when you equate chemical potential of A in alpha and liquid. Do the same thing equating chemical potential of B. This is the second equation, this is the third equation, and parallelly we also have that the atom fraction, if you add up A, B, C in liquid, it should be equal to 1. If you add this up, it should be equal to 1. So, now look at how many unknowns we have. We have, so each of these A, B, C, N A, N B and C, they are unknown. So, you have 6 unknowns, but how many equations do we have? We only have 5 equations. So, therefore, if you want to solve this, it is impossible to solve. So, that is why, you know, if you look at this composition triangle at a particular temperature, if you are able to, if you want to solve this, say suppose we have seen at a particular temperature, this side let us say alpha, this side is liquid, this is alpha plus liquid. You want to find out at particular composition which phase is more stable. How can you do it? So, in that case the best way to do it is to construct or find out that free energy, which will be a mixture of say weight fraction of let us say alpha, the total free energy, this total will be the free energy of, let us say, this is the liquid and this is weight fraction liquid plus weight fraction solid, the free energy of alpha. You construct this. Now, you try and find out, you change these weights and try and see and minimize and what values of these weight fraction is this minimum, and this can be done in a computer easily. So, what you have to do? You are trying to solve at every point on this composition triangle and find out which combination of that percentage of certain places. Suppose here you will find if it is 100% solid, then the free energy is minimum. Here if you find that 100% only if it is 100% liquid, it is that free energy is minimum, but in between you will find you have to say that here it will vary. I mean so similarly you will be able to find out here both can coexist. In that case you can construct this boundary. So, this is how the computation or phase equilibria problem is solved in a higher order space. Now, if you extend the same thing in the case of eutectic, what will you have? Now, in that case what you can do following the exactly that similar case in a ternary eutectic, what you can write at that eutectic temperature, let us say just above that eutectic temperature, say you can equate as say N A in alpha, this will be equal to N A in liquid plus that N A liquid, then exponential F A. So, you will have the three such equations. You have three such equations and we will also have, and here let us try and simplify it even further. We assume that alpha is pure A. So, that means we assume this is equal to 1. Similarly, N B beta, this is equal to 1, N C gamma equal to 1. So, that means what we are assuming that liquids in the liquid state A, B, C, they form an ideal solution, whereas in solid state they are totally insoluble in each other. And in that case, if you take up, let us say some numerical values, this is the melting point of A, this is the latent heat of fusion for A, this is melting point of B, this is latent heat of fusion for B, this is melting point C of C, this is latent heat of fusion of C. Now, in that case, now let us see what do you have here. You have, if you apply the phase rule, we have seen that P plus F equal to C plus 1. So, here this number of component is 3. So, this is equal to 4 and here liquid is breaks down into 3 solid, mixture of 3 solid. So, you have a situation where 4 phases are coexisting. So, therefore, degree of freedom equal to 0. So, that means not only, I mean this can happen only if the temperature is fixed, and therefore, it should be possible to calculate the temperature in principle, and this is what is shown over here. If you equate this ternary eutectic, that estimation of that eutectic temperature, these are the 3 equations. Now, here you assume that this portion this is equal to this is 0, you can say that this equal to 0, this is a stable phase, it is pure A, this is 0, and in that case what you need to do here, you see this is N A plus N B plus N C, they represent atom fraction A, B, C in liquid, they should be 1. So, what you need to do? You need to iterate, it is a simple iteration process. You change this temperature, only unknown is this temperature here. Now, change this temperature to satisfy, that is N A plus N B plus N C equal to 1. If you do this, you will get this exact temperature. In this particular case is this. Now, you try, if you make all these equal, if you make this temperature, this also you make 1200, this also you make 1200, then you will find that all these points N A, N B, N C, they all will be equal, 1/3, 1/3, 1/3. Now, I will one point is here, if you see this, you will be situation, you will come up with situations where you often have to, in this ternary diagram or in a multi component system, you often may have to apply that material balance here, say where 3 phases are coexisting, so or multiple phases are coexisting, how you do it. So, here also the principle will be exactly similar to that of that composition triangle concept that we have seen, and which is shown over here. This is, say, suppose U V W, and you have an alloy of this composition, and so what will be the percentage of this phases U V W. So, they will be present in this ratio U V W. Now, look at how much is W. So, W will be proportional to W will be proportional to this part. So, W will be proportional to here, and these 3 will constitute an equilateral triangle. So, here also you can imagine, so you draw lines which are parallel to each of these lines. So, W is equal to this from here to here, which is equal to m n. Similarly, V is equal to, from here U m is equal to V, and U is equal to V n. So, which is shown over here. So, with this, therefore, we now finish just seen the case of that equilibria in a multi component system. We looked at ternary system in detail, and higher order system becomes much more complicated, and with certain simplifying assumption and assuming solution model like ideal solution model, I just said it is possible to calculate that ternary eutectic temperature, and in a very specific system we did that calculation, and same thing can be used for higher order systems. And in fact, there are nowadays thermodynamic databases using that program which minimizes that by minimizing free energy, that minimization of free energy concept, it gives you solutions that in certain composition phases with the available thermodynamic data, what is the expected number of type of phases and their composition, it is possible to calculate. And two very common these packages, they are known as one is a thermocalc, fact sage, there may be others also. So, in short, What we looked at today, we looked at composition triangle, looked at ternary isomorphous diagram, we looked at vertical and horizontal sections, we looked at ternary eutectic, we looked at its several vertical and horizontal sections. We applied phase rule to see that whether it is applicable here. We looked at ternary eutectic calculation has been done, and we also looked at how this concept can be extended to understand equilibrium in higher order systems, and there in all probability you have to resolve to thermodynamic databases with solvers, which are there are commercial packages available like Thermocal, FactSage. Thank you very much.